Okay. Yeah, so thanks for giving me a chance to come and talk about this. This is actually a bit of a throwback for me. This is some work I did as a graduate student while I was at Scripps. So it involved a number of people, actually. You can see Travis Davis at the time was an undergrad at UCSD. My advisor was Maddie Morsfeld, and then Kathy Constable, that's with us, was on my dissertation committee. This is actually a part of my dissertation, so you'll have to forgive me if I have some flashbacks to my defense today, especially if Kathy asked me a mean question at the end or something. Oh, okay, okay. And then also involved were Alex Fournier and Gautier Lowe at IPGP. And then now I'm over at University of Maryland and NASA, Goddard Space Flight Center. Okay, so what I'll do, or what I'll try and do, is give you a little bit of the motivation that started this project. So this topic's going to be, maybe a little bit different from what everyone's been talking about this week here, but hopefully everyone will find it interesting. So I'll give the background of how we got into this work, and then two different ways we started trying to look for precursors or things that allow you to predict reversals and excursions. And then I'll give some wrap-up remarks and sort of, this is a project that I left behind a couple years ago, but I think there's a lot that could still be done with this. And so I can tell you a little bit about some of my ideas of how this might be picked back up and moved forward by somebody. Okay, so the idea really came from thinking about the sort of casual remarks that people make about reversals and excursions over coffee and tea. So these are things that we probably a lot of us in this room have said before casually and not really thought about whether there was much of a basis for it, right? So, the popular science question the general public wants to know sometimes when they learn about the reversing field is this going to happen soon, right? Again, and people say things like, well, no, the axial dipole, it's still strong relative to the recent past, so it's not going to reverse anytime soon. Or you say, well, the strength of the axial dipole is actually decreasing quickly, so let's do something naive and just draw a line through it, and yeah, we're on our way to a reversal, right? And then, of course, there's the classic gambler's fallacy. It's been 780,000 years, so of course it's going to happen, right? And so you hear these kinds of things, but then we wondered, well, is there really any basis for this? And really implicit in all those statements is the idea that maybe there's somehow a precursor to reversal, something about the axial dipole at a given time that sort of tells you whether or not one is about to happen. Okay, so what we really did is reframe the question and just say, can you look at the axial dipole and predict when a reversal or excursion is going to happen? You can say whether or not you think it's going to happen sometime in the near future. And then, like any good problem where the question is very simple to ask, you sit down and start trying to think of ways to go about answering this, and you realize, oh, there's actually a lot of issues here. You have to be very careful to define exactly what it is you're trying to predict. What do you mean by a reversal or an excursion? Okay? And of course, the other thing, this was brought up after the last talk, is that you don't really have a lot of good data on the Earth if you want to use machine learning, like I'll talk about in the second half of this talk, right? So what I'm going to do is I just cheat. I just use simulations, okay? And then we'll look at some paleomagnetic reconstructions, but we'll do a lot of exploration with simulations. Okay, so I'm going to talk about what we ended up calling threshold-based predictions first, because that really sets up the framework for the machine learning stuff later on. So this will be a really simple, straightforward way of trying to test prediction strategies, but it'll help us set up the machine learning stuff. So the first thing, as I said, is you need to come up with a careful definition of exactly what it is you're trying to predict. So we ended up clumping reversals and major excursions all together into something we decided to just call a low dipole event. Okay, so this is just a cartoon of an axial dipole time series with the sign indicating polarity. And we're just going to say that an event starts when you drop below what we'll call the start of event threshold, and then that single event is ongoing until the axial dipole recovers beyond this green line here that we're calling the end of event threshold, right? And the idea is that you don't want to sit there and count all these little zigzags where you change sign quickly or something like that. We're not trying to predict all those as somehow individual reversals. And of course, since we're going to work with simulations, we actually have the benefit of getting good we can get whatever temporal resolution we want. So we can actually, in my fantasy world where I don't have to work with real data, right, I can see every little wiggle that I want. And so we clump all those things together and just call them single events. So there are two events in this picture. Okay, and I should say, what we're going to do with all of these is we will, in all the simulations and the paleomagnetic reconstructions we look at, we will normalize the intensity by the average value of the simulation or the reconstruction. So that will just be the average intensity will be 1, and the start of event threshold is going to be 10%. Okay, so once the dipole gets very low, and the end of event is when it recovers back to 80%. So what happens is those choices may seem arbitrary, but what I can tell you is that we went and used different choices within a reasonable range. And what happens is, though some of the raw numbers will change, qualitatively everything I will talk about and show you today basically stays the same. Okay, so the results aren't particularly sensitive to these choices. And then we'll also have the event duration. That's just the length of time that a particular event takes. So how long it takes after it drops down below 10% to recover to 80%. Okay, so it's not showing up too well in this projector, but just as an example, this is a 3D time series from a simulation I'll talk about in a second. So this contains four distinct events in it, right? So again, we're just avoiding counting multiple times all these changes in polarity that happen quickly as the dipole's low. Okay, so here's the collection of simulations we'll look at. So we have these 4 models. We have G12, that's just a simple system of 3 ODEs. One of them represents the axial dipole. We also have 2 stochastic differential equations, P09 and DW, and then 3D, so that's actually a full 3D dynamo simulation that exhibits polarity reversals. Okay. And then with the threshold pace predictions, we just do the simplest thing you can imagine. Okay, I'm just going to pick something I'll call a warning threshold. I'm showing you this red horizontal line. And we'll just say when the intensity drops below the warning threshold, right, we start saying, I think a reversal is going to happen within, and then we have this prediction horizon. I've labeled pH here. So this is another thing where what we did was we chose a prediction horizon that's equal to the average event duration. Okay, so for the paleomagnetic reconstructions, that's about 10,000 years. But again, this is another thing, like the start of event threshold and the end of event threshold. Qualitatively, the result, we tried other things, 50% of that, 150% of that. Qualitatively, these results don't change. So all these choices, the results aren't going to be particularly sensitive ultimately to them. Okay, so you walk along and at every point in the time series of an axial dipole, you just make a prediction whether or not a reversal is going to happen within the prediction horizon, right? And so at every point, the prediction is either a true positive, yes, you're correct, a reversal is going to happen, a false positive, you predict something's going to happen, but then it doesn't, or true negative, false negative. So you want to evaluate how well this works. So you need to use some sort of skill score. So there are a lot to choose from with a bunch of different acronyms, right? They're not all equivalent. In this problem, you have imbalanced data, right? A reversal or a major excursion is rare. So most of the time you would be correct for a reasonable prediction horizon, so something like 10,000 years. You'd almost always be correct to say a reversal or major excursion isn't going to happen in the next 10,000 years, right? So you don't want to use, the reason that I bring this up on the slide, you don't want to do something naive like use accuracy, because this is a problem where it's very easy to achieve high accuracy. Just always predict nothing's going to happen. You're right more than 99% of the time. So We ended up using what's called the Matthews correlation coefficient, MCC score. This is one that's commonly used in cases of imbalanced data, so it's more robust to this situation. So it's going to force us to try and make good predictions of these rare events. And then the sorts of things we're going to do is, for example, this threshold strategy, we just go to a simulation of this G12 model, and we try a bunch of different warning thresholds, and we figure out what maximizes this MCC score. And then you can take that warning threshold and apply it to independent simulations from the same G12 model for validation, okay? And then you can see here, this is the sort of thing you get when you apply that warning threshold to this validation data sets. So you find in the case of the G12 model, something like 30% is your optimal warning threshold. Okay, so I have these four different models that give me simulations, and it turns out the prediction skill then with this simple threshold strategy varies widely among these models, though they're meant to be modeling the same thing, right? So here I show a bit of the time series of the G12 dipole, and then below that is the prediction. So it's 0 when the warning threshold's predicting no reversal is going to happen. And then it goes to 1 when I do predict something's going to happen, and then in the bottom it just shows the truth, what that plot should look like, right? So here they match up almost perfectly. It's very easy to predict G12. It's well behaved. The stochastic model P09, it's a little bit more difficult. You have some false positives in there, some false negatives. DW is even harder, and 3D is the hardest. So you look at this and you say, well, you've come up with a very complicated way of identifying how wiggly a time series is, right? That's not that interesting. But actually, something interesting is happening here. With this MCC skill score, it's not all these false positives that are really killing us. When you dig down, what happens is the really damaging thing to your skill score is all these false negatives, times where a reversal is about to happen and you don't realize it. So it's all these places where you're late in recognizing what's going on with the warning threshold. And if you look a little closer, what you see is something that's been observed by others before. It has to do with how rapidly these models decay versus how quickly they recover. Okay, so the G12 model that's really nice and smooth and well behaved, it actually decays quite slowly and then recovers quickly. So if you look on the left there, the green dot is where the intensity drops below 80%. Just as a reference point, I go ahead and use the end of event threshold. The yellow dot is where the event begins, so where I get to 10% of the average intensity. And then the red is where the event ends, where I've recovered back to 80%, right? So long, slow decay, rapid recovery. The complete reverse of that is true for the 3D model. For this full 3D dynamo model, when it undergoes reversals, on average, it looks more something like this, right? The decay is sudden, it's very rapid, and there's this long, slow recovery. So in fact, if I go and I plot the average decay time, so the average time between the green and the yellow dot there, over the average event duration, how long it takes to recover, right, you get this plot on the lower left. And then on the lower right here, you actually see these MCC skill scores, how predictable these models are using this threshold-based strategy. They qualitatively, they really reflect this sort of asymmetry in that how rapidly the models decay versus recover, okay? Okay, so with the thresholds, the prediction skill varied widely depending on what simulations you were going to look at. There's this notable asymmetry in the decay and the recovery that differs among them. And then the question is, where do paleomagnetic reconstructions fall? So we looked at PAD M2M and SINT 2000. And in this case, of course, we have very, very limited data. So I just used the first section of the time series, or the older section in both of these reconstructions for training. And then I just have in the validation set the two most recent reversals. And here you can just see I'm zoomed in on that validation. You know, it falls somewhere in the middle of all these models, okay? So It's not as hard as say the 3D model, but it's not as straightforward as G12. And so these are the actual skill scores here. This is the plot I showed before, but now on the right-hand side, I've added the skill scores for Pad M to M and Cent 2000. You see again, they're somewhere kind of in the middle. And if you look at the decay time in these models compared to the recovery, that's also the situation. So here, again, this is I've shown these numbers over here before that show the average decay time over the event duration. This horizontal line is a ratio of 1, right? So everything above this line, it decays more slowly than it recovers. And that is the regime that Pad M to M and Cent 2000 are in. Okay, so that was the first thing we did, and that really set up the framework for trying to apply machine learning. So now I use the canonical example for classification of machine learning, right? Is that you have a bunch of pictures of dogs and cats. This is all going to be supervised stuff. You have them labeled as dogs and cats. You feed them into your neural network and you do your training. And then what you hope is that now I can feed it a picture of a new dog, right? And then hopefully it recognizes what it's seeing. So of course that requires a lot of data. And this is something that's difficult when you have imbalanced data. You have way more cats than dogs. We want to do this now with reversals and excursions, right? So we'll still rely on our hierarchy of models because of this limited data issue. And then because the data are imbalanced, we'll have to adjust the training process for these machine learning algorithms. All right, so this is basically the plot I showed before. Now we don't have a warning threshold on here. The setup's going to be very similar. Instead of having a warning threshold, what I'll have is this search window, this segment of the recent dipole time series that I'll look at. And that's the thing I'm going to try and classify. I'm going to use the same sort of setup, event duration, prediction horizon, all these things. I'm just going to look at segments of the time series and try and classify it as, yes, this precedes a reversal or excursion within the prediction horizon, or no, it doesn't. So we tried a couple of different methods here. The first thing, the simplest thing, is just support vector machines. These are really, this is really a straightforward idea. You just have some n-dimensional object. You try and create some hyperplane in that space. If you just have a binary classification problem, you just try and create some hyperplane that divides the two classes up. Okay. But this is a good example of something that with imbalanced data, it's going to just err on the side of always predicting nothing interesting is going to happen, right? No reversal or excursion is going to happen. So during the training of, for example, an SVM, and we'll do this with the other methods that we tried, what we do is in the cost function during the training, we reduce the penalty for false positives relative to false negatives, right? So we don't punish it as much for raising its hand and saying, yeah, I think a reversal or excursion is going to happen, because otherwise it'll just never do it. And this plot is a good example of why you do this SVM training plot over here, right? So on the horizontal axis is the size of the false positive to false negative penalty ratio in the training cost function. And then you can see in orange across the top is the resulting accuracy you get from the SVM that you've trained. Again, it's almost always going to be 100% because these are rare events. But we're using the MCC score. That's what we actually want to maximize. That's shown in the teal right there. And you can see that somewhere around a 0.5, a ratio of 0.5, you tend to maximize the MCC score. So that's how we'll do our training with the machine learning. We'll use this little tweak. We'll go through. We'll actually find the algorithm that we train that maximizes the MCC score when we vary this ratio. All right, and so remember the whole idea is to try and see if we can actually spot precursors to these events. So what does that even look like, or what is that going to look like? So we're going to have this search window I showed where we look at a segment of time series and try and classify it. And actually what we do is we vary the size of that search window. And so if I start out with just a threshold prediction strategy like I had before, say, and I get an MCC score, so the search window size is basically 0. You're just looking at one point in time. If I get MCC score indicated by that purple dot, if I then start to expand the search window, I give this classifier longer and longer segments of the recent history of the dipole. If it's flat, that really means it doesn't seem to be finding anything. Predictions aren't getting better by looking into the recent history of the dipole. On the other hand, if we get something like that red line where we start to see an increase as we give it more information about the recent past, that's an indication that that's clear evidence that it's found some sort of precursor. Okay, so the very first thing we did, we don't want to worry about training data size problems yet or anything. So we just start with a large simulations from the G12 and 3D models. So this is the easiest and the hardest one to predict. Okay, the dashed lines just show the result of just the threshold prediction strategy. And then the dotted lines show what you get out of, in this case, it's just a linear SVM. And so in G12, you do see this pattern where it increases. You add more information about the recent past. But in the case of 3D, it's flat. And actually there are, there's this little wiggle here where it dips down, and this doesn't quite line up with a threshold. This just has to do with how fine the grid is of when we adjust the false positive to false negative penalty ratio. If you took more time to train this, you could land right on the threshold strategy. Okay, so it does find precursors in this simple G12 model, but what does that really mean? What's it doing? So as I said, that model is just a simple system of 3 ODEs. We're just feeding it information about the axial dipole, the D in that equation. But it looks at that, and obviously it infers something about Q and V. In this case, they're supposed to be representative of the quadrupole, and something about the fluid velocity in the outer core. Okay. So do we really believe that there aren't any precursors in the most interesting model that is this 3D simulation? So we look a little more into this. You'll notice I haven't said anything with the machine learning stuff yet about the two SDE models, the two stochastic models that I looked at in the threshold case. That was DW and P09. That's because those, by construction already that there's nothing in the history of those that's going to help you make predictions. Okay, the present intensity of the dipole in those models completely dictates what's going to happen next. I mean, plus there's this random component to it. Okay, so there's no benefit to looking at the recent history. As a sanity check, though, we go ahead and train the algorithms on this and see exactly what you'd expect, right? All the machine learning methods, there's no benefit to looking at the recent history. You don't ever do any better than a threshold strategy. So the question really is the 3D model the same sort of thing when you just look at the axial dipole? You can't really prove a negative, but you can keep digging and you keep coming up with the same answer. You start to get suspicious that maybe there really isn't anything in there hiding in the axial dipole 3D model, and that certainly seems to be the case here. So now instead of support vector machines here, this is actually using a long short-term memory network. It's a type of recurrent neural network. And you see, again, with this same sort of algorithm, you get this flat line as you expand the search window. You do no better than a threshold strategy still. Okay, and so we look a little closer at the time series in a more traditional way. So here I'm computing the correlation between the step that the dipole of the simulation takes and lags with the previous steps, okay? So in the G12 model, you can see that the step that you're about to take in intensity is still heavily correlated with the distant past. That's not surprising. We've seen that it's a predictable model. On the other hand, with 3D, you see something that looks an awful lot like what you would get out of these SDEs that have no memory, right? It looks like the step that the 3D simulation is about to take in terms of axial dipole intensity doesn't have any connection to its recent behavior. So this also lends credibility to our suspicion. I think that there's maybe no precursors in this simulation. One other thing we looked at is, okay, let's just suppose we have something, a process, the Earth itself somehow is still very predictable, but we only have something like 5 well-resolved reversals or major events like this. Is that even enough to train a simple machine learning algorithm on where it would find something meaningful? So we take that G12 model, that's always our sanity check since it's so well behaved and predictable. You give it a short time series with only 5 reversals in it, you train an SVM, right? And then you go and apply that to independent validation data, and you see this horrible thing where the skill score actually drops, right? It's just, there's probably just simply not enough data right now of high enough quality, of high enough resolution to really successfully train a model to try and identify precursors for the actual Earth. Okay, so G12, again, very well behaved. You can predict reversals by looking in the recent history of the model, but we didn't find anything like that. It's a very simple model. Once you move to the 3D simulation, we don't see anything. So even though I just told you the data is probably too limited, we've already got all this machinery set up. So let's go ahead and just apply it to the paleomagnetic reconstruction, see what comes out. So in this case, because the data is so limited, we do a 5-fold cross-validation, right? So you chop things up into 5 segments of time series, and you train on 4, leave 1 out for validation, right? And then you just repeat this 5 times, each time leaving a different data set out. And then we have the threshold skill score there in the dashed line, and we compute a standard deviation of the 5 scores we get just to get an idea of how wildly they're jumping all over the place. This is with SVMs. And we also tried it with LSTMs, but basically you get the idea that this is too short of a time series and the variation is too great to really say anything definitive. The threshold skill score is always within this very broad standard deviation. Okay, and so then we go back to this sort of plot and add PAD-M and Cint 2000, and it's kind of the same case as we saw with the threshold-based predictions, where these correlation plots sort of look somewhere in between G12 and the stochastic differential equations. Okay, so what are the conclusions here? Certainly this machinery is able to identify precursors in this really well-behaved model with 3 ODEs, but that's a very simple model. And already with that, you really have to have a very long simulation to avoid some sort of overfitting in the machine learning that you're training. I think one of the most interesting things here, though, is looking at this detailed physics-based model, the 3D simulation, and really finding that there wasn't any evidence of these sorts of precursors in the dipole. And so if you believe that 3D simulation really is an accurate reflection of the Earth, which if you're familiar with dynamo simulations, that might be a pretty big if. But then there's indication that maybe you're not going to find precursors in the dipole, Earth's actual axial dipole. It does suggest, for what it's worth, that these simple SDE models for the axial dipole, they, at least statistically, they look a lot like what you get out of a full expensive 3D dynamo simulation. And then we didn't find any convincing evidence of precursors in the paleomag reconstructions, but that's, of course, as I said, that data is very limited. I don't know that you could, even if they were there, based on our experiments with the simpler models. Okay, so where does this go from here? As I said, this is something that I left behind a little while ago when I was done with my graduate work, but I think there's more to do here. So the idea is to set up this framework of looking for precursors, but recast as this problem of making predictions. Now that this machinery is set up, I think the thing that really should be done is to start looking at, with this 3D simulation, adding more features of the system. Because of course, I mean, it's a simulation, so nothing stops us from looking at higher order terms of the observable field. You can look at the quadrupole and things like that. And also, I mean, really, it's still not well understood, even in these simulations, they're so chaotic, what really precedes these reversals. Is there specific things that characterize what goes on in the dynamo simulation right before a reversal? So while these machine learning methods that I'm using here, unlike the physics-informed neural networks, are a bit of a black box, you can imagine a scenario where you might take the simulation and now start feeding it different pieces of the simulation, features of the physics, even things about the flow in the interior. And at least at some point, you'd expect that one of these algorithms might be able to start predicting an imminent reversal, and based on what information you're feeding the system, that might tell you something about what characterizes the behavior of the dynamo right before reversal, whether that has to do with the fluid flow or something in the higher degree observable field at the surface. And with that, I'll stop.